There we go. All right, I'm actually got my presentation up. So this is sort of a continuation of kind of the first two times you all heard me talk. Um, what I'm going to talk about is um how we're kind of applying some next generation thinking. So again, I'm John Kaczala. I work at Nokia. I am driving the OCP Telco Edge project. Um, so this is kind of part of the team that we have at Nokia has been looking at the application of liquid cooling into the open edge platform and looking to see what benefits are possible. So in terms of the open edge, this is a continuation of a presentation that they did last year, I believe. It was kind of more theoretical at that point, and so since that time, uh, we've actually been at work to actually put this together. So what we've been looking at doing was applying a direct-to-chip liquid cooling approach on the server. So this would be kind of a mixed air and liquid cool solution to see, what benefits we could get out of liquid cooling parts of the system and how to kind of bring that to fruition. So this doesn't completely put together a full solution. It's just kind of I would say, a little more of a prototype. It would need some more evaluation in terms of how would you tie this all together and say the rack and that type of thing. So this is kind of looking at it from the sled perspective. Um, so what we did is this required kind of a modification to kind of to the sled, and I'll kind of talk about that in a bit. But really the goal was to try to make this, again, backward compatible with what's out there and kind of make all of this work and the constraints that we have in that system, and to really kind of show the potential of taking this concept and technology further. And kind of building on what kind of the theme of OCP Summit is, this is where I think some of the work that's going on in some of the other groups can really be synergistic to, what's happening maybe here in our little slice of the world. So that's really our goal, is to try to foster that collaboration and, work with, perhaps others in OCP and really kind of drive this technology into this small, high-performant form factor. So, at present, everything was done through an air cooling approach. Um, and, these are kind of the specifications to bring that together. So, what we did is we looked at what we could do with sort of the 1U server. And so the study adapted a pump direct-to-chip liquid cooling solution, working within sort of the heat density available, and then establishing this development on that platform, and looking at this more of an evolutionary approach. So we kind of added to it as we went along. So to start with, we just looked at what would happen if we could just liquid cool the server. So this was sort of the minimal impact to a lot of the rest of the system, and see just what that did and how it was considered in terms of a component that was most critical to these cooling needs. Sort of also as a side effect, it was interesting as just cooling the server also had sort of a locality impact to cooling other parts of the platform as well. So we kind of looked at what you could do as sort of a hybrid of air cooling and liquid cooling, and playing with different rates of, say, coolant flow and fan speed, and looking to see what could we do with, say, the acoustics of the system itself. Typically, these telecom platforms are a little bit noisy, and we wanted to see, hey, could we actually get this down to like something that would be compliant to what would be a an office environment type of decibel level. So the details about our key requirements were put together in a white paper that was contributed to Open Compute. So if you're interested in more details, that would be here. And so we initially focused on the 1U server. If you remember, there's also a 2U, but our goal was to kind of understand what was the behavior on sort of the smaller server first, and then possibly take this forward. And we looked at it in terms of the 3U chassis. So the proof of concept design was based on updating the server sled and chassis, but really trying to keep any kind of modifications to a minimum. So we tried to build on some of the modularity that's already been put in the system itself. So this is sort of what the default server sled looks like. So you'll see on the right there are 4 fans, and basically there's a heat sink. So what we looked at doing is replacing that heat sink with a cold plate, and then you'll see what we did is we took out one of the fans and put in a set of manifolds where we could then pump the coolant in and out of that cold plate. And this is what it looks like from the back of the chassis itself. So you'll see that one of the fans was replaced, and we now have that set of manifolds that can then be connected to a CDU, for example. And then this is sort of what the system would look like then from sort of the whole back of the rack perspective. And the design was such that you would hook these, so each sled itself is independently liquid cooled, and that they would be pumped in parallel, so that every one of them was kind of a separate standalone environment. So from the feasibility perspective, the system was informed with CFD simulations. So we kind of looked at it first to understand kind of what the flow could be through the cold plate and at these chassis level manifolds, and to optimize that for equal fluid distribution. And then the validation study was conducted in a physical proof of concept system, allowing for testing and performance analysis. And so kind of what you see here is sort of what our findings were. So if you look on the left, those orange bars, that is the system at a stressed level. In the red area there, and kind of a baseline idle on the left on the blue. And so what you'll see is the system was designed to handle the CPU at its maximum load, but still stay within the constraints of the specification and the CPU, such that we didn't incur any overheating. But you can see that it actually does bump up pretty close to maximum there. And so what you'll see is with the liquid cooling, we were able to bring that down quite a bit. And so those are the blue bars. So you'll see that we could pretty much almost cut that in half. So that gives us a lot more headroom now in terms of thermal capacity within the platform. And then what you'll see on the right there, this was looking at the VRM temperature. So you'll see that even this had an impact there as well. Not quite to the same extent that you had at the CPU, but there was still a benefit there. So one of the things that we looked at was what could we do with this? So this liquid cooling solution opens the possibility of increasing the thermal design of what we can actually do within the constraints of the current specified system. Allowing tests to be conducted with a full OEE chassis containing, say, up to 5 1U servers, and up to 270 watt CPUs. So the system was initially cooled by a liquid flow at 25C with a flow rate of 2 liters a minute. And so the system shows reliable operation with no leaks. We had it testing for over about 200 hours. Of course, because some of the concerns are, are we trading off more complexity by adding liquid cooling, through leaking, through additional componentry that needs to pump the liquid, those kinds of things, and where is the economic trade-off? So we looked at reliability, and it seems that it still was quite stable. So the liquid cooling also helped the CPU cool the board itself. That was also a benefit. So what it did was allow us to run the fans at quite a reduced amount of speed and duty, which also allowed us to reduce the number of fans. So that actually reduced the sound level. So if you'll see there at the chart on the right, I believe anything below 50 decibels is can be considered kind of office equipment level. So you'll see on the green in the far right graph there, the green is at 48.8 with 2 fan modules at 10%. So we can actually cut the fans down quite a bit, which cuts down a lot of the noise, and actually gets this into some decent area of even audio pollution, if you will. So it's not just heat pollution, but audio pollution as well. So what are some of the things that this enables? So this gives us the potential to reduce the energy consumption. Since the liquid has a much better heat transfer property than air, and also enabling the use of free cooling systems. It improved cooling allows the increase of the system density, so that we could actually put within that limited space that we have, higher density CPUs, memory, storage, even different types of accelerator cards, both at the system level and server level, increasing the CPU performance, and perhaps even more server sleds within that same footprint. It also reduced the air cooling dependence, so we could actually lower those fans quite a bit, also cutting down on energy, and having them run at a much more acceptable noise level. And then also better thermal stability. So you'll see that, if you remember the charts from before, we had a much more consistent performance as to retaining the system at a specific temperature, so that theoretically that will preserve and extend the life range of the components themselves. So that would reduce not only cost, but also maintenance and repair. And then finally, as most as the heat that in the system is being generated by the CPU, being able to collect that could be used for other uses for, say, heat recovery. So moving forward, while this study showed the potential of applying liquid cooling to the OpenEdge platform, some things still need to be thought out and developed, and could perhaps evolve in our standards. So, like I said, this is mostly focused at the sled level and with minimal change. It could be interesting to see, taking this to the next level. If we start to have to bring in things like GPUs and the other types of accelerators, how could this design be extended? And then finally, what would be kind of the specifications and things how do you go ahead and handle, the heat exchange outside of the sled itself, from at the CD level. Also too, what could be the long-term performance analysis of these liquid cooling systems? So, we ran, about a 200-hour test. But probably the next step would be to run this at a much longer duration to kind of prove these things out in a more extended life cycle. So also taking this and exploring this beyond, say, the server components, but things such as the DIMMs, PCIe cards, etc., And then finally, improving the understanding of the challenges related to liquid cooling in an edge environment. So, I think people are pretty familiar with air cooling, but what would this really look like, with these remote deployments? So just to kind of just talk about the project a little bit. So that was the chassis, and we did this to the 1U server sled. But the whole solution then would consist of the front hall gateway, and then our next steps would be to look at what could we do with the 2U server. And then finally, call to action. So again, I invite everybody, join us in the telco OCP project and in the Edge project. We'd love to have more of you get involved and help us all kind of take this to the next level. And with that concludes my talk, and I thank you very much.
Cool. Questions? Any questions? Who's brave here to talk about cooling questions? New topic, so it's not easy questions, right?
Well, coming from Texas, I need a lot of cooling.
Yes,
so.
There you go. Oh, there. Why don't you come to the mic in the middle, please? Right here. Yeah, come in the middle right there.
Oh, there he is.
Hello.
Hello.
I did have a question. So it seems like there's a lot of technical advantages. In terms of costs, is that something that you guys have taken a look at? Like, I know you save on like the BOM cost for removing a fan, but then you add in the cold plate, right? But then you have lower overall server power consumption. Does it edge out in the end of being cheaper overall, or what does that look like?
Yeah, so I think looking kind of the business case, right? So there may be some additional upfront cost, but that's kind of CapEx cost. And what this would bring you is more OpEx, more longer term life cycle for all of these pieces, right? And the worst enemy to a lot of electronic computer parts is heat and thermal variation. And so by keeping the thermals consistent and keeping them at a much cooler temperature, it will should extend the lifespan of all of those. So I think it's kind of taking it, maybe putting a little bit more up front on the cost perspective, but you'll gain a lot more in the whole life cycle. And then plus, being able to say clock these things up as well, you can actually get also more performance out of it.
Sounds good. Thank you.
Any more questions? All right. Well, thank you very much. And, again, please join us on the Telco and Edge OCP projects. We'd love to have more of you involved. I think that would be fantastic.
All right. Thank you.
Thank you very much.